program.
So, okay, right now, let us start the session. So, we are in the second module, network theorems and network topology. So, in previous class, we discussed about the superposition theorem, Norton's theorem, and Thevenin's theorem. So, till now it is completed. So, today we are going to discuss about the maximum power transfer theorem. Let us see. Right. So the statement for maximum power transfer. What is maximum power transfer theorem? Right. So according to this maximum power transfer theorem, in a circuit which is connected to a DC voltage source, it will deliver the maximum power to the load, which is a resistive load, when the source resistance is equal to the load resistance. Now, if you see this circuit, so this is the circuit. So in this circuit, you have your voltage source and you have a source resistance, you can say this, and you have one load resistance RL, right? Now, this source, which is having some internal resistance RS, will deliver some amount of power to this load RL, right? So now here, at what condition the maximum power will be delivered to this load RL? So will be given by this maximum power transfer theorem. Okay, according to maximum power transfer theorem, this voltage source will deliver the maximum power to the load RL. So whenever the value of load resistance RL will become equal to the source resistance RS. Okay, whenever load resistance is equal to the source resistance, so which is RS this value, so then the maximum power will be delivered to the load RL from the source. Okay. Right, let us see the proof for maximum power transfer theorem. Okay, according to the maximum power transfer theorem, the source will deliver the maximum power to the load whenever load resistance will become equal to the source resistance. Now let us see here, if you take any big circuit, right, so you will be having one load. Okay, so this load actually connected between two terminals A and B, let us say, and the remaining circuit will be this one, so which is a two-terminal linear circuit. Okay, so now this two-terminal linear circuit will be having many sources also. So you may be having two sources or three sources. Again, it may be current sources, voltage sources, and even you have some resistances also. Okay, so now it is a two-terminal linear circuit. Now from this circuit, you will get the power to this load RL. Okay. Now, whatever may be this two-terminal linear circuit and whatever may be the elements in the two-terminal linear circuit, you have to replace this two-terminal linear circuit with 1 volt in series with the resistance here. Okay, so in this format, you have to bring your circuit. Okay, you will be having two terminals A and B here. Between A and B terminals, you will be having the load resistance, and the remaining circuit you should bring to with this format, V Thevenin'S in series with R Thevenin. That means here we are going to use the Thevenin's theorem. Okay, so according to the Thevenin's theorem, any big circuit, any circuit, if it is given, it must be replaced with one voltage source in series with the resistance. So the same procedure here also we are going to follow. Okay. Right. So let us see the proof for the maximum power transfer theorem. Now you have to replace any two-terminal circuit on the left side of your load resistance with the Thevenin's equivalent circuit. Okay. So to get this maximum power transfer theorem condition, first you need to derive the Thevenin's equivalent circuit for given circuit. Okay. So this is the Thevenin's equivalent circuit for your two-terminal linear circuit. Okay, so this RL will be replaced as it is here. Okay, now the amount of power so dissipated across the load resistor is given by this current flowing through this load resistance I square into RL will be the power across the load PL. Okay, so this source will deliver some amount of current. This current will flow through the load resistance RL. Now power across the load resistance will be PL is equal to I square into RL. So this is the total power dissipated across the load. Now, if you want to determine the current flowing in the circuit, now in this circuit, current flowing through this circuit from the source will be equal to I. So which is I is equal to the source voltage V Thevenin by total resistance. So total resistance here in the circuit is R Thevenin plus load resistance RL. Okay, so total current you determine. Total current will be equal to source voltage V Thevenin by R Thevenin plus RL. So now this current we are going to substitute in here, so that PL will become PL is equal to, so in place of I, this will get V Thevenin by R Thevenin plus RL, and it is having square into RL. So the value of PL will be equal to V Thevenin by R Thevenin plus RL whole square into RL. Okay. So now if you derive this, so V Thevenin square you can separate it. So then you will be having RL by R Thevenin plus RL whole square. So let it be equation number 3. Now you need to get the condition for maximum power transfer theorem. Okay, so according to maximum power transfer theorem, when source load resistance will be equal to source resistance, then maximum power will be delivered to the circuit. Okay, so to get this is the power equation, the load power equation. Now to get this maximum load power, what you need to do, you have to derive this PL with respect to a variable term RL, and it must be equated to 0. Okay, we are differentiating the load power PL with respect to load resistance RL, which is a variable parameter, and equating it to 0. So this from this you will get the maximum or minimum value. Okay, so you can get either maximum value or minimum value. So here our intention is to determine the maximum value. Okay, so if you are given any equation from the mathematics, you know that so to get the maximum or minimum value for that particular function, so you need to derive that particular function with any variable parameter and equate it to 0. Okay, the same we are going to apply here. Okay, so here this is the load power. So PL is equal to V Thevenin square into RL by R Thevenin plus RL square. Now to get the maximum power, this equation 3 we are going to differentiate with respect to RL and equating it to 0, so that you will get the condition for maximum power transfer. See here. So in place of PL here, we are going to substitute this equation V Thevenin square into RL plus R Thevenin by RL square. So this can be written as differentiation of d by dRL into V Thevenin's square multiplied by RL by R Thevenin's plus RL whole square. Okay. So now it will be equated to 0. So now here you have the two terms. Okay. So you know d by dx of two terms, f of x and f of y. So that you have to apply here. So then you will get this equation. So V Thevenin square is equal to R Thevenin plus RL whole square into 1 minus RL plus RL into 2 into R Thevenin plus RL by R Thevenin plus RL whole power 4. Okay. So you should remember this now, d by dx of V Thevenin's. So in previous slide, what is this? V Thevenin's square into RL, one term. So V Thevenin's into square into RL, one term, by so R Thevenin's plus RL whole square. Okay. So you call this as some y. We call this as some z. Now d by dx of y by z. How we can write? So this equation is denominator will be having z square So this value. Now y into dz by dx minus, you have to keep it z as it is. Now you have to differentiate y with respect to x. So this is the equation. Okay. So this equation you have to apply here. Okay. So then here in place of it, you have the RL. Okay. So from previous slide, here you have to differentiate this total expression with respect to RL. So here in place of it, you need to take RL. Now, so from this, what you can write? So this will be equal to. So now here in denominator, you will be having R Thevenin's plus RL whole square. So now according to this square, whole square you will get R Thevenin's plus RL whole square, whole power again square. Okay. So now you take this term or this phi term, R Thevenin's plus RL whole square, you keep as it is denominator term, and you have to differentiate this numerator with respect to RL. So V Thevenin's square into RL. So minus, and numerator keep it as this. Again differentiate with respect to RL the term which is R Thevenin's plus RL whole square. Okay. Right. So now here R Thevenin's plus RL whole square. So now if you differentiate this term, so V Thevenin's square into RL. So what you will get when you differentiate this, you will get V Thevenin's square only. Okay. So V Thevenin's square into R Thevenin's plus RL you will get. Okay. So this here. So in this term, V Thevenin's square is there. Here also V Thevenin's square is there. So they are taking the common. So then you'll be having R Thevenin's plus RL whole square into, so d by dRL of RL will be, it will be 1 minus, as V Thevenin's is going gone outside. So you'll be having RL into 2 into RL into d by dRL into R Thevenin's plus RL whole square. So we are going to differentiate this. If you differentiate this, what we will get? R Thevenin's plus RL 2 into you will get. Okay. RL into 2 into R Thevenin's plus RL. So this you are getting here. So RL into 2 into R Thevenin's plus RL whole divided by, so this R Thevenin's plus RL whole power 4. Okay. So this is how you can derive this expression, and this value should be equal to 0. Okay. So now this total expression to become 0. So what should be 0? This numerator term should be 0. Okay. So in this expression, if this numerator term is equal to 0, so then only you will get the value of 0. So we are equating this R Thevenin's plus RL whole square minus 2 into RL plus, 2 into RL into R Thevenin's plus RL will be equal to 0. Okay. So now from this expression, again we are deriving this. So here you'll be having R Thevenin's plus RL. Here also you have R Thevenin's plus RL. We are talking about one term, R Thevenin's plus RL. So that here you will be having another term, R Thevenin's plus RL. Here you will be having minus 2 RL. Okay. So now from this expression, we can take this equation, R Thevenin's plus RL equal to 0. Then this total expression will become equal to 0. Okay. So then, so here this now. So from this expression, R Thevenin's RL minus 2 RL you are having. So from this R Thevenin's minus RL. So from this R Thevenin's plus RL you will get, which will be equal to 0. Now this again can be written as R Thevenin's square minus RL square is equal to 0. So this can be written as R Thevenin's square is equal to RL square, or you can even write it as R Thevenin's is equal to RL. You can derive like this also. Okay. So from this expression, the condition for getting maximum power is RL is equal to R Thevenin's. Hence, it is proved. Okay, according to maximum power transfer theorem. So this theorem states that the load will get maximum power. So whenever the source resistance will become equal to load resistance. If you take one simple circuit, so here you have the voltage source, and this voltage source is having internal resistance RS. Okay, so this is practical voltage source. Now here you are having the variable load. Okay, this load will be changing here. So now, so this load will get the maximum amount of power. So whenever this load resistance RL will become equal to RF according to the maximum power transfer theorem. Okay. Right, any doubts here up to this? Okay, so now, so what is the value of maximum power? Okay, so as from the maximum power transfer theorem, the maximum power will be delivered from source to load whenever the value of load resistance will become equal to the value of source resistance. Okay, so now what is the value of this maximum power delivered to the source? That means we are going to calculate the value of the amount of maximum power. Okay, so for calculating this, in place of RL, you need to substitute R Thevenin's. So according to this theorem, RL will be equal to RS. So in place of RL, so we are going to, so as I mentioned before here, so we have here, so any linear circuit will be replaced by one Thevenin's equivalent circuit. Okay, so now this Thevenin here, this Thevenin's resistance will be the same as source resistance. Okay, so this V Thevenin's can be, you can assume it as a VS, source voltage. Okay, so now in this circuit, the maximum power will be delivered to the load RL. So whenever this load resistance RL will be equal to RS. So RL is equal to RS is nothing but RL will be equal to R Thevenin's. Okay, so here to get the maximum amount of power, we are going to substitute here in place of RL, R Thevenin's, and in place of PL max in the equation 3. So equation 3, what is this equation 3? So equation 3 is the amount of maximum. So it is the power delivered to the load. Okay, this is the power delivered to the load. Okay, PL is equal to V Thevenin square into RL by R Thevenin plus RL square. Now to get the maximum amount of power here in this equation, in place of PL, we are going to write the PL max. And in place of RL, we are going to write the R Thevenin's. Okay, so here in place of RL, we are going to write R Thevenin's here and here. So then what we will get? So PL max is equal to, so V Thevenin square, in place of RL, you are getting R Thevenin. So here also R Thevenin you are getting. So we derive this again. So V Thevenin square is equal to R Thevenin by, so this value is 2 into R Thevenin whole square. So this you can write it as 4 into R Thevenin square. So this value. So now this R Thevenin, one value you can get cancelled. So the maximum power delivered to the load will be equal to V Thevenin square by 4 RTH. Okay. So if you want to calculate the amount of maximum power delivered to the load, then you have to use this equation. Right. So PL max is equal to V Thevenin by 4 RL. Also you can write. Right? Why? Because according to this maximum power transfer theorem, this R Thevenin may be same as RS, RL. Okay, so both are the same. Okay, if you in problem, so they will give the load resistance. You can use this equation also. So PL max is equal to V Thevenin square by RL. So if the load resistance is not given, you can use this equation. V Thevenin square by 4 R Thevenin. R Thevenin you will determine from the Thevenin's theorem. Okay. So the maximum amount of power transferred to the load from source will be either of this equation, V Thevenin square by 4 RL or V Thevenin square by 4 RTH. Okay, so remember this equation. Now, if you determine the efficiency under maximum power transfer condition, so what is the value? So let us see. So efficiency is nothing but, so this will be equal to output power by input power. Okay, so if you take the same circuit, here you are having the V Thevenin's, and here you are having the R Thevenin's. So this is equivalent circuit, Thevenin's equivalent circuit, and terminals A and B you are having. And here across these two terminals, you are having load resistance RL. Okay. So now the current delivered from the source is, let it be I, and the value of I will be equal to V Thevenin's by R Thevenin's plus RL. Okay. And power delivered to this load RL. So load power RL PL will be equal to, you can even write it as I square into RL. Okay. And power delivered from the source PS will be equal to I square into R Thevenin's plus RL will get. Okay. So power input or power coming from source, both are the same. Okay. Power input will be equal to, so power delivered by the source. So this value will be equal to I square into total resistance R Thevenin's plus RL. Okay. So now power output is nothing but power across this load resistance, right, which is the P out. So power output is equal to power across the load resistance RL. So here current flowing through this RL will be same as I only. Now this I square into the load resistance RL you have to consider. Okay. See here, source power PS will be equal to I square into R Thevenin's plus RL. So this value you can even write it as I square R Thevenin's plus I square RL. Okay. So now according to maximum power transfer theorem, so this RL can be equal to R Thevenin's. So in place of RL, you can write the R Thevenin. So the input power will be equal to 2 into I square into R Thevenin's you will get. Okay. And output power will be equal to this value. So PL is equal to I square into RL. Now this even can be written as, so PL is equal to I square into RTH. Okay. In place of RL, you can write it RTH. Why? Because under maximum power transfer condition, RL will be equal to RTH. Now this is the output power and this is the input power. So the efficiency will be equal to output power by input power. So which is 2 into I square RTH by I square RTH. Sorry, output by. I have written in reverse. The efficiency is equal to output power is I square into RTH. Input is 2 times I square into RTH. Now these two will get cancelled. So the efficiency you are getting 1 by 2. Okay. So 1 by 2. So if you want the percentage of efficiency, you have to multiply this with 100. So that you will get the 50% efficiency. Okay. Under maximum power transfer theorem condition, so you will get the efficiency as 1 by 2. So which is in percentage, it will be equal to 50%. Okay. So this is about the maximum power transfer theorem. So you have to remember here the condition first. RL is equal to RS or R Thevenin. Okay, according to the maximum power transfer theorem, so maximum amount of power will be delivered to the load. So whenever this load resistance is equal to the source resistance. So here for a linear two-terminal network, this source resistance we can take it as a Thevenin's equivalent resistance. Okay, and maximum power delivered to the load. So PL will be equal to V Thevenin's square by 4TH. So this was derived here. Okay, so this one maximum power delivered to the load will be equal to V Thevenin's square by 4RL or 4TH. So this you have to remember. Okay, or this even can be written as I square into RL also, or I square into RTH. So power across the load. Okay, let us see one problem or one example so you can understand. See here the problem, find the maximum power that can be delivered to the load resistance RL for the circuit shown in figure below. Okay, so this is the circuit given here. Now in this circuit you are having a load resistance RL. Okay, so this load resistance is a variable resistance. Okay, so now they are asking the maximum power delivered to this load. Okay, how you can determine the maximum power? So let us see. Okay, so you keep this RL terminals as A and B as it is. So these two terminals are A and B. Now the remaining circuit, for the remaining circuit, you have to apply the Thevenin's theorem. Okay, for this total circuit, you have to apply the Thevenin's theorem. So Thevenin's theorem is already done. Okay, so by applying the Thevenin's theorem, this entire circuit you have to replace with one voltage source in series with the resistance. Okay, so this is called the V Thevenin's and this is called the R Thevenin's. Okay, so now across these two terminals, finally you have to connect the load resistance RE. Okay, so now maximum power will be delivered to the load whenever load resistance will be equal to source resistance, which is here R Thevenin, and power delivered will be equal to PL is equal to V Thevenin squared by 4 RTH. Okay, so like this you can determine. Now, so here our first aim is to determine the Thevenin's equivalent circuit across these two terminals A and B by keeping this RL as it is, or you can even remove this, so that across these two terminals A and B you can write the Thevenin's equivalent circuit. Okay, how you can determine the Thevenin's equivalent circuit? So here so here you have so 20 volts source, and here you have the 5 ohm resistance. Here you are having 10 ohms resistance. Here you are having 10 ohm resistance, and one current source is also given here. Okay, now between these two terminals A and B, you need to represent the Thevenin's equivalent circuit. Okay, this total circuit you have to replace with one single voltage source V Thevenin's in series with the R Thevenin. Okay, so what is the value of R Thevenin? How you can determine this R Thevenin? According to Thevenin's theorem, if there are any voltage sources, those voltage sources has to be short circuited, and current sources will be open circuited. No, so from this circuit, so for determining the Thevenin's resistance R Thevenin, so unmute now. Mute yourself. Okay, right. First, you need to determine this R Thevenin's, right? So this R Thevenin's you can determine by short circuiting the voltage sources and open circuiting the current sources. Then this circuit, this entire circuit can be written as only 5 volts, 5 ohms here, 10 ohms, and here 10 ohms will be there. So this current source will be open circuited, and this current voltage source will be short circuited here. So here this is short circuit. Now when current source is open circuited, so you no need to consider that. So now here you will be having the terminals A and B. So now between these two terminals A and B, you need to find the equivalent resistance. So that equivalent resistance will be same as your R Thevenin's, right? So now from this circuit, so 5 ohms is in parallel with the 10 ohms, and this combination is again in series with the 10 ohms. So 5 ohms in parallel with the 10. So this total value, if you sum with the 10 ohms, this, so you will get the R Thevenin's value. Okay. So now parallel combination of these two, how you can write 5 into 10 by 5 plus 10 plus 10. Okay. So 5 into 10, 50 by, so this value 15 plus 10 you will get. So now this can be written as, so 50 plus maybe 150 by 15 you can write. Okay. So this will be 200 by 50. Okay. So this can be written as 100 by, so it will not go to 100. So 200 by 15 you are getting here. Okay. So 5 ohm in parallel with the 10 ohm. So once you do with your calculator, so 5 into 10 by 5 plus 10 plus 10. Okay. So you do this total, you are getting R Thevenin's will be equal to 40 by 3. So you do with calculator. Okay. R Thevenin's you are getting 40 by 3. Okay. So then another thing is you need to determine the V Thevenin's also. Right. So V Thevenin's is the open circuit voltage across the terminals A and B. So between the terminals A and B, you need to determine the open circuit voltage. This will be equal to the V Thevenin's. Right. While determining this open circuit voltage or V Thevenin's, you need to keep as it is all the sources. Okay. So then here I will represent the same circuit. So one voltage source here, it is having the resistance here, and here you have the current source. So between the terminals A and B here. Okay. So what is the source value? 20 volts, current value 4 amps. Right. So this voltage source value is 20 volts and current is 4 amps. Okay. And resistance are 5, 10, 10. So this is 5 ohms. So this is 10 ohms and this is 10 ohms. Okay. So between these two terminals, you need to determine the open circuit voltage, which is called the V Thevenin's. Okay. So for determining the V Thevenin's or open circuit voltage across the terminals A and B, you can use any method. Okay. So now here these terminals A and B are open circuited. So the current flowing to this 10 ohms will be same as the 4 amps. Okay. Here also the 4 amps only you will get. Okay. So now here you can apply the nodal analysis. Okay. Here how many nodes are there? This is one node and this is another node. So this you can consider it as the ground node, and this node will be node 1. Here you consider the voltage to be V1 and find the value of V1. Right. So now I'm considering the currents are flowing out of this node, all the currents. So according to nodal analysis, this V1 minus 20. So V1 minus 20 by 5 plus V1 by 10. So plus, actually here if you see, you know the current flowing to this 10 ohms, so which is 4 amps. Okay. So now our assumed direction is from left to right, and the actual current is going from right to left. So this current you can consider it as a minus 4 amps. This will be equal to 0. So now from this circuit, you will get the value of V1. Okay. So here 1 by 5 plus 1 by 10, 1 by 5 into V1 minus 20 by 5 minus 4 will be equal to 0. So this can be written as, so this 15 by, so 10 you take common. So you take, you will get 2 plus 1 into V1. So here 5, 4 you will get, so that you will get 8 here. So V1 will be equal to 8 multiplied by 10 by 3 you will get. So 80 by 3 is your nodal voltage. So here. So V1 at this node. So V1 value you are getting. So 80 by 3. So now you need to determine the voltage across this. Okay. Voltage across this is nothing but voltage across this point and this point. Okay. So now here you need to get the voltage across this. So now let it be here. V Thevenin's will be the voltage at this point A. Right. So now here you have the V1. So between this V1 and V Thevenin, we have this 10. And current flowing to this is 4 amps. Okay. So current is known and voltage difference between the two terminals is known. Okay. Then, so that current I will be equal to V Thevenin's minus V1 by 10 you can write. Okay. So I is the 4 amps, and V Thevenin's value you need to determine, and V1 value is already calculated, which is 80 by 3 by 10. So this can be written as, so 40 is equal to V Thevenin minus 80 by 3. Okay. So from this, V Thevenin's can be written as 40 plus 80 by 3. So this can be written as, so 120 plus 80 by 3. So total you will get 120 plus 80, 200 by 3. Okay. So V Thevenin's value is 200 by 3. Okay. So R Thevenin's value already calculated, so which is 40 by 3, and V Thevenin's value you are getting here is 200 by 3. So that we are going to substitute in the Thevenin's equivalent circuit. Okay. So this is the Thevenin's equivalent circuit, which is having one voltage source V Thevenin's in series with the R Thevenin's. Now between these two terminals A and B, you need to connect the resistance, load resistance. Okay. So between the terminals A and B, we are going to connect the load resistance RL. Right. So if any circuit is given, first you need to convert that circuit into in this form. So by using the Thevenin's theorem. Okay. So now you need to determine the power across the load RL. So power across the load RL will be equal to PL is equal to I square into RL, you can write. Okay. Or directly you can use the equation. So while we derive in the, already we derived, so that value is V Thevenin's square by 4 RTH. Okay. So this is the maximum power. So this value is the maximum power. So this is this you will not get. So maximum power delivered to the load will be equal to V Thevenin square by 4 RTH. Directly you can use, or by using this expression you can also derive also. Okay, as we already derived, so you can use direct formula. So PL max will be equal to V Thevenin square by 4 into RTH, and the value of V Thevenin is known, and the value of R Thevenin is also known.